A single drop of liquid gallium can compromise the integrity of a structural aluminum beam within hours. While aluminum relies on a dense, face-centered cubic crystal lattice for its high strength-to-weight ratio, gallium exploits a specific vulnerability at the microscopic level. Gallium remains liquid at just 29.7 degrees Celsius, allowing its atoms to move freely. When this liquid touches aluminum, it does not simply sit on the surface like water. It initiates a process of rapid diffusion that targets the weakest points of the metal's internal architecture. This interaction is not a standard chemical reaction that creates a new compound throughout the book, but rather a surgical strike on the bonds holding the crystalline grains together. Understanding this requires looking past the shiny metallic surface and into the thermodynamic forces that drive liquid gallium into solid aluminum. Aluminum exists as a polycrystalline material, meaning it consists of millions of tiny crystals or grains. These grains are oriented in various directions, meeting at regions called grain boundaries. In a pure aluminum structure, these boundaries are held together by strong metallic bonds. However, gallium atoms possess an atomic radius and electronegativity that allow them to slip into these boundaries with minimal energy cost. As gallium atoms penetrate the lattice, they disrupt the cohesive energy between aluminum atoms. Because gallium has a significantly lower melting point and different valence electron configuration, it cannot maintain the structural rigidity required for the aluminum to remain a solid. The gallium atoms effectively act as a lubricant at the atomic scale, replacing strong aluminum-to-aluminum bonds with much weaker interactions. This specific type of intrusion transforms a ductile metal into a brittle substance that can be crushed by hand.
The phenomenon occurring here is scientifically classified as liquid metal embrittlement. This is a specific form of environmental degradation where a normally ductile metal loses its plasticity and tensile strength when exposed to certain liquid metals. For aluminum, gallium is the ultimate embrittler because of its high solubility at grain boundaries and its low surface tension. The liquid gallium reduces the surface energy of the aluminum grain boundaries, a process described by the C and Hondros model of grain boundary enrichment. This reduction in energy makes it thermodynamically favorable for the gallium to spread throughout the internal network of the metal. Unlike corrosion, which involves the loss of material through oxidation or chemical consumption, liquid metal embrittlement is a physical transformation of the bond characteristics. The aluminum remains chemically present, but its macroscopic structural properties are completely neutralized by the presence of the foreign atoms. Aluminum is naturally protected by a transparent, highly stable layer of aluminum oxide, also known as alumina. This ceramic layer is what prevents aluminum from reacting instantly with oxygen and water in the atmosphere. To destroy the aluminum, gallium must first bypass this protective skin. If the oxide layer is perfectly intact, gallium may sit harmlessly on the surface. However, any microscopic scratch, thermal stress, or mechanical deformation provides an entry point. Once the gallium makes contact with the raw aluminum metal beneath the oxide, it begins to spread laterally. It moves underneath the alumina layer, lifting it away from the metal substrate and preventing the aluminum from reforming its protective barrier. This creates a self-sustaining cycle of penetration. As the gallium moves deeper into the structure, it opens new paths for more liquid to follow, effectively tunneling through the material from the inside out. The speed at which gallium destroys aluminum is driven by the physics of grain boundary wetting. In metallurgical terms, a liquid is said to wet a boundary if the energy of the liquid-solid interface is less than half the energy of the original grain boundary. Gallium exhibits an exceptionally low dihedral angle when in contact with aluminum grain boundaries, often approaching 0 degrees. This means the liquid gallium is pulled into the metal by capillary forces, much like water being absorbed by a sponge. This movement occurs at speeds far exceeding standard bulk diffusion. In some aluminum alloys, gallium can migrate through the material at rates of several millimeters per hour. As the gallium film coats each individual grain, the macroscopic object loses its ability to transfer mechanical load. The grains are no longer bonded to each other, they are merely floating in a thin film of liquid gallium. Temperature plays a dual role in the destruction of aluminum by gallium. First, the gallium must be in a liquid state, which occurs at approximately 30 degrees Celsius or 86 degrees Fahrenheit. If the environment is colder, the gallium remains a solid and the embrittlement process is significantly slowed, though not entirely stopped due to solid-state diffusion. Second, as the temperature increases, the kinetic energy of the atoms rises, accelerating the rate at which gallium atoms migrate through the grain boundaries. This relationship follows the Arrhenius equation, where the rate of diffusion increases exponentially with temperature.
In industrial environments or high-friction zones where aluminum components operate at elevated temperatures, the presence of gallium is even more catastrophic. Even a trace amount of gallium that might be stable in a cool climate can suddenly become a liquid and cause a structural collapse if the machinery heats up during operation.
Not all aluminum is created equal when it comes to gallium sensitivity. High-strength aerospace alloys, such as those in the 7000 series containing zinc and magnesium, are particularly vulnerable. These alloys often have complex grain boundary chemistries designed to inhibit dislocation movement, which provides their strength. Gallium exploits these specific microstructures more aggressively than it does with pure aluminum. In contrast, the 6000 series alloys, commonly used in structural frames and containing silicon and magnesium, show slightly different rates of penetration, but are still ultimately susceptible to failure. The presence of alloying elements can sometimes create intermetallic compounds that gallium preferentially attacks. This makes the use of gallium near any engineered aluminum component extremely dangerous, as the specific heat treatments used to harden the metal often create the very grain boundary conditions that gallium is most efficient at infiltrating. When an aluminum component treated with gallium is subjected to stress, it fails through intergranular fracture. In a healthy piece of aluminum, a crack would typically propagate through the grains, a process known as transgranular fracture, which requires a massive amount of energy to break the atomic bonds of the crystal. In a gallium-invested sample, the crack follows the path of least resistance along the liquid-filmed grain boundaries. This requires almost zero energy compared to the original state. The metal does not bend or deform before breaking. It simply shatters or crumbles into a fine gray powder consisting of individual aluminum grains. This lack of ductility is the hallmark of liquid metal embrittlement. Because there is no visible deformation prior to the final collapse, it is impossible to detect the impending failure through visual inspection until the structure is already compromised beyond repair.
The interaction between gallium and aluminum is a major security concern in the aviation industry. Modern commercial aircraft are constructed primarily from high-grade aluminum alloys due to their weight and durability. If gallium were introduced to the structural airframe, such as the wing spars or fuselage skin, it could lead to a catastrophic mid-air failure. For this reason, gallium is strictly regulated by international air transport authorities and is often classified as a hazardous material. Small spills of gallium in the cargo hold of an airplane have historically required the removal and replacement of entire sections of the aircraft floor and support beams. The risk is not just from intentional sabotage, but also from improperly packaged scientific equipment or mercury-free thermometers. Once the gallium starts to spread, the only solution is to physically cut out the contaminated metal, as the diffusion cannot be easily reversed or neutralized. Dealing with a gallium spill on aluminum requires immediate and specific action. Because the diffusion process begins the moment contact is made, the liquid gallium must be removed as quickly as possible. Mechanical suction or freezing the gallium to return it to a solid state can slow the damage. However, because the gallium moves beneath the surface oxide layer, simple wiping is often insufficient. In laboratory settings, specialized chelating agents or chemical washes may be used to bind with the gallium atoms, but these are often ineffective once intergranular penetration has reached a significant depth. Prevention is the only reliable strategy. Professionals working with gallium must use secondary containment systems and ensure that no aluminum tools or surfaces are present in the work area. The permanent nature of the structural damage means that any aluminum parts touched by gallium are generally considered scrap and must be recycled through smelting to remove the impurity.